So this is vector calculus, the last class, lecture 26. And it's really for review, but I want to start with the problem that I got stuck on Monday because I kept making some arithmetical mistake, but after a while, you can always fix it up, I think. So let me turn to that, which is on Green's theorem, section 17.4, exercise 19. So let me remind you, first of all, what is the circulation form of Green's theorem? So there are two forms, but we're just looking at the first, which is called the circulation form. And it says the following. It says if you have a line integral around a closed curve of a vector field, it's the same notation as the text. dr. So F, which is F comma G, is a vector field. So to every vector, the vector field assigns a new vector. And C is a simple closed curve enclosing some region R. So we always have this picture. We have this curve C, and it's always oriented in the positive direction, which means if you imagine walking along the curve, your right hand is sticking out and your left hand is sticking into the interior. So the line integral of the vector field around this closed curve is the double integral over R of a function which is called the curl of the vector field. So this is the partial of G with respect to X minus the partial of F with respect to Y, where little f and little g are the coordinate functions of the vector field. So we have this region R enclosed by a curve, and the double integral of this expression, which is called the curl of F, it's the two-dimensional curl, is equal to the line integral. This is convenient and useful for many reasons. Sometimes you need to calculate one, but it's too hard, but you can calculate the other. So you solve your problem that way. And in exercise 19, so this is exercise 19, F is the vector field minus 2xy, comma, x squared. So f of xy is the first coordinate minus 2xy. G of xy is the second coordinate, x squared. So the curl, which is the partial of f with partial of g with respect to x minus the partial of f with respect to y. You differentiate this with respect to x, you get minus 2y. If you differentiate, if you differentiate g, x squared, with respect to x, you get 2x. And if you differentiate f with respect to y, you get minus 2y. You get minus 2x. This is minus 2x, which is 2x plus 2x, which is 4x. So if we have to do the right-hand side integral, the integral over r of the curl, we're integrating 4x dA. So if we write this as an iterated integral, I have to say what is the region. The region R is bounded by the curve y equals x times 2 minus x, parabola. So this is the region R. So x goes from 0 to 2. And for every x, y goes from 0 to x times 2 minus x. So this is the right-hand side of Green's theorem. So 4x is like a constant. So this is the integral from 0 to 2 of 4x times, when you integrate 1 from 0 to x times 2 minus x, you get x times 2 minus x. You get x squared times 2 minus x dx. So now we're back to Calc 1. This is the integral from 0 to 2 of 8x squared minus 4x cubed dx. This is the integral from 0 to 2. Sorry, this is 0. The integral of 8x squared is 8/3 x cubed. The integral of 4x cubed is x to the 4th from 0 to 2. So we get 64, 8 times 8, 64 over 3 minus 16, which is 48 over 3. So we get 16 over 3. And so this part we did on Monday. So again, let's draw this picture. This is my region R. This is R is the region given by x goes from 0 to 2, and y goes from 0 to x times 2 minus x. And the double integral over R of the curl 4x dA is 16 over 3. So we want to compute now the line integral, the integral around C of f dot dr. And C, if we go around this curve in the positive direction, we start at 0, 0, we go to 2, 0, and then we go back around and up in this way. So this integral along C of f dot dr, and let me just call this the part of the boundary from along the x-axis, I'll call that C1, and the part coming back along the parabola, I'll call C2. So this is the integral along C1 of f dot dr, plus the integral along C2 of f dot dr. Okay. So are there any questions about this? This is just setting up the Green's theorem problem. So C1 is easy to describe. C1 is just the curve that just goes horizontally across this base of the region. So let's say R1 of t, it's just t comma 0, t goes from 0 to 2. At 0, you're at 0, the origin, you just walk across. So C1 is this line, and the integral around C1 f dot dr is the integral. It's an integral with respect to t. T goes from 0 to 2. F, remember our vector field is minus 2xy, x squared. So F is equal to minus 2xy. G is equal to x squared. Along this function, along this curve, x of t is t, y of t is 0. So this is the integral of f dx plus g dy. This means the integral from 0 to 2. What is f of xy? 0. So f of x of t, y of t is minus 2 x of t, y of t. The y of t is 0, so this is 0. G of x of t, y of t is x squared. That's t squared. T squared. And dy dt, but y of t is 0, so dy dt is 0. So this is just the integral of 0 plus 0 dt, which is 0. So the integral along this horizontal line is just 0. So the work in the problem is to compute the integral along C2. So C2 starts at the point 2, 0, ends at the point 0, 0. And what is this function? So R2 of t is going to be, so I want t to go from 0 to 2. And as t goes from 0 to 2, the x-coordinate of this curve goes from 2 to 0. So this is simply, we can write this as 2 minus t. And this is the curve y equals x times 2 minus x. So when x is equal to 2 minus t, we get 2 minus t times 2 minus 2 minus t. We get 2 minus t times t. That's the y component. So this is x and this is y along this curve. So let me see if I can do the integral correctly this time. So the integral along the curve C2, the top of the curve, f dot dr. This is the integral as t goes from 0 to 2. F of t dx dt plus g of t dy dt. So f is equal to minus 2xy, which is minus 2. X is 2 minus t. Y is 2 minus t, it makes that squared, times t. G is x squared is 2 minus t squared. So this is the integral from 0 to 2, f of t minus 2t, 2 minus t squared, times dx dt. X is 2 minus t, so dx dt is minus 1. And dy dt, y is 2t minus t squared, is 2 minus 2t, or 2 times 1 minus t. So it's minus 2t, 2 minus t squared, plus g of t, 2 minus t squared, times dy dt, which is 2 times 1 minus t dt. This is the integral from 0 to 2. I have 2 minus t squared times minus 2t So why is this a minus? Oh, sorry. F of t is minus 2t, 2 minus t squared, times dx dt, which is minus 1, makes this plus 2 times 1 minus t dt. This is 2t plus 2 minus 2t. These cancel, so this is 2. So this is simply 2 times the integral from 0 to 2 of 2 minus t squared dt. And the integral of 2 minus t squared is minus t, 2 minus t cubed over 3, evaluated from 0 to 2. When t is 2, this is 0. When t is 3, when t is 0, I get minus times minus is plus. 2 times 2 cubed is 2 to the 4th. 16 over 3 is 16 over 3. So we get that the integral around the closed curve is the integral around C1 plus the integral along C2, which was 0 plus 16 over 3. So we get 16 over 3. And that's exactly what we had gotten on the right-hand side. So just being a little bit more careful with my arithmetic, we get the right answer. That is our example of greenstone. Any questions about this? Any questions about any of the problems that we've had in Math 226? Any of the homeworks? Review sheet, practice exam?
Professor, are we going to go over the practice finally?
Well, I'm saying I'm here to answer any questions that you want to ask. So if you want me to go over
can you go over the practice?
yeah, sure. So let me pull it up if I can.
Thank you.
Just to make sure I have the right thing. So I believe, so this is the final exam review. So I think in problem 1, we have two vectors, minus 3j plus 4k, and v is minus 4i plus j plus 5k. And what is the cosine of the angle between them? So we have these two vectors, u and v, and there's an angle between them. So we know that the dot product of any two vectors is the product of their lengths times the cosine of the angle between them. So the cosine of theta is the dot product over the product of their lengths. The dot product is 0 times -4 plus -3 times 1 plus 4 times 5. The length of the vector u, square root of 3 squared plus 4 squared. Length of the vector v is square root of 4 squared plus 1 squared plus 5 squared. So this is -3 plus 20, 17. This is the square root of 25, which is 5. This is 25, 26, and 16. Is that right? 16, 17, and 25. So if my arithmetic is correct, the cosine of the angle between these two vectors is 17 over 5 times the square root of 42. And if this is the vector v, and this is the vector u, this will be the projection of u in the direction of v. So how do we find the projection of u in the direction of v? So just to show you sort of how one gets such a formula, if this were a and this were b and this is theta, then a over b is cosine theta. So a is b cosine theta. And what is a? So if we take the cosine of theta is what? Cosine of theta is the length of u. No, it's the dot product of u and v divided by the length of u times the length of v. And b, the length of b, this is the length of u. So this is u dot v over the length of v. That's the magnitude of this projection. And in the direction of the unit vector in the direction of v. So in general, the formula for the projection of a vector u in the direction of v is the dot product of u and v over the length of v squared times v. So I never remember this formula. I always have to work it out, but this is the formula. So what is the dot product of u and v? We just calculated that. That's 17. What is the length of v squared? The length of V is the square root of 42. So the length of V squared is 42 times the vector V, which is minus 4I plus J plus 5K. So that is the projection of U in the direction of V. Any questions about that? So the start of the semester was just learning about vectors in 2- and 3-dimensional space. That formula actually works no matter what the dimension of the space is. But problem 2 is to calculate some limits. What is the limit of xy over x plus y as xy approaches the point 1, 1? Well, as xy approaches 1, 1, x times y approaches 1, and x plus y approaches 2. So the limit is just a half. Part B may be a little trickier. We take the limit as xy goes to minus 1, 1 of x squared minus y squared over x squared minus xy minus 2y squared. Now, as x approaches 1, minus 1, and y approaches 1, the numerator goes to 0, and the denominator also goes to 0. So you can't just plug in x and y equal to minus 1 and 1 respectively. But let's see. X squared minus y squared, we know how to factor. That's x minus y, x plus y. What about x squared minus xy minus 2y squared? Does that factor? This might be equal to, if I'm lucky, let's see, x minus 2y times x plus y. I get x squared minus 2xy plus x. Yeah, that works. So this is the limit as xy goes to minus 1, 1 of x minus y, x plus y over x minus 2y, x plus y. And the x plus y's cancel. So for xy different from minus 1, 1, but getting closer and closer to it, the numerator goes to minus 1 minus 1, which is minus 2, and the denominator goes to x minus 2y minus 1 minus 2 minus 3, or 2/3. So it looks like the limit is equal to 2/3. Problem 3, we have a function of 2 variables. F of xy is 3x squared y to the 5th. Partial of f with respect to x is just 6x y to the 5th. If I take the second partial derivative of f, first with respect to x and then with respect to y, or in the other order, the order doesn't matter for a continuous function. If I differentiate this with respect to y, I get 30xy to the 4th. And if I want to take the second partial derivative of f with respect to x twice, I just differentiate this again with respect to x, which is 6y to the 5th. So these are the answers. Any questions about this? Let's see, problem 4. We have w is z times the log of x squared plus y squared. where x is a function of t, y is a function of t, and z is a function of t. And the chain rule says that dw dt is the partial of w with respect to x, dx dt, plus the partial derivative of w with respect to y, dy dt, plus the partial derivative of w with respect to z, dz dt. So we have to calculate these 6 derivatives. The partial of w with respect to x, when I differentiate this with respect to x, I get z over x squared plus y squared times 2x times dx dt, which is 3e to the t. When I differentiate this with respect to y, I get 2 over x squared plus y squared times I get z, that's a z over x squared plus y squared times 2y times dy dt, which is 4e to the t. And when I differentiate this with respect to z, I just get the log of x squared plus y squared times dz dt, which is 1. And then I have to substitute in what are the values of x, y, and z with respect to t. I have 6 x times z times 3e to the t. So I get 9 e to the t. I get 2, let me just write 2 times 3e to the t times t times 3e to the t over x squared plus y squared, 9e to the 2t plus 16e to the 2t. And I plug in for the other terms as well. And then when I calculate these things, the first term is 6 times 3, which is 18, t e to the 2t over 25 e to the 2t. These cancel. My first term will be 18t over 25. And then you do the arithmetic for the other terms as well. So, that's
Professor,
just,
sorry.
yes,
Can you move the paper over slightly?
over slightly.
Sorry, can you move it a little more to the right, please? Yeah, thank you.
But this is just, at this point, it's just Calc 1. Here the lesson is really to make sure that you know what the chain rule is and how to apply it. That's all we're doing. Okay. So that's the chain rule. Problem 5, we have the function f of xy is x over y squared. The gradient of f is the partial of f with respect to xi plus the partial of f with respect to yj. When you differentiate this with respect to x, you get 1 over y squared I. When you differentiate this with respect to y, you get minus 2x over y cubed j. So that is the gradient. And the gradient of f evaluated at the point 0, 3 is when x is 0 and y is 3, you get 1 over 9i, and this is 0, so it's just 1 over 9i. And to get the directional derivative of f in the direction of the vector u, so u is the unit vector √3 over 2, 1/2, and this is a unit vector. You can check that the length of u is √3 over 2 squared plus 1/2 squared is 3/4 plus 1/4, which is 1. So if the square of the length is 1, the length is 1. And and the directional derivative is, let's see, there are various forms in which I can do this, and I just always want to take the notation that's used in the text. It's really just a dot product of the gradient with the direction. So the gradient is 1/9 at this point 0, 3, 1/9 I, dot product with u, which is √3 over 2i plus 1 over 2j. So that dot product is just √3 over 18. So that is the directional derivative. I think these are all sort of like basic things from the beginning. So we have the gradient of f, the gradient of f at 0, 3, and the directional derivative of this function at 0, 3 in the direction of this unit vector. Okay, that's problem number 5. Problem number 6, we have a surface, which is a kind of ellipsoid, x squared plus y squared over 4 minus z squared over 9 equals 1. And if you take the point P with coordinates 1, 1, 3/2, and does it lie on the surface? Let's see. 1 squared plus 1 squared over 4 minus 3/2 squared over 9 is 1 plus a fourth, and this is 9/4 over 9 minus a fourth equals 1. So this point does lie on the surface. And so we have some surface, and on this surface, you have the point 1, 1, 3/2, and we want to find the tangent plane to the surface going through this point. And the tangent plane is the plane through this point perpendicular to the gradient of the function at this point. You have a function f of x, y, z equal x squared plus y squared over 4 minus z squared over 9. The surface, this surface, is the level curve. All the points where f of x, y, z is equal to 1. And the gradient of this function is 2x, first coordinate, 2y over 4, which is y over 2 is the second coordinate, and minus 2z over 9. So the gradient of f at the point 1, 1, 3/2 is 2, 1/2, and when z is 3/2, it's minus a third. So we want to find the equation of the plane through this point with this normal vector. So the tangent plane should be given by the system of equations 2 times x minus 1 plus a half y minus 1 minus a third z minus 3/2 equals 0. So this is 2x plus a half y minus 1/3 z minus 2 minus a half is minus 5/2 plus a half is minus 4/2 is minus 2. So bring it to the other side equals 2. So if I take 1, 1, and 3/2, I have, when x is 2, when I have 1, 1, 3/2, this is 2 times 1 plus a half times 1 minus a third times 3/2. That's 2 plus a half minus a half is 2, right? Perfect. So that's the equation of the tangent plane. Well, if you don't like fractions, you could write it as multiply by 2, multiply by 6. Well, don't have to. That's the equation of the tangent plane. Okay. Any questions about this? Now, how do you get a linear approximation to a function of two variables? So this is simply the two-dimensional case of what you did in Calc 1 when you had a one-dimensional linear approximation to a function of one variable. So if you have a function of one variable, y equals f of x, that's the curve, and at some point, you want to approximate it by a straight line. So this is the curve, y equals f of x. This is the linear approximation. Say this is the point a comma f of a. You simply take the tangent line to the curve at this point. So the tangent line would be the line through this point where the slope is the derivative. So it's y equals f prime at a, x minus a, plus f of a. That's the tangent line to a curve. And in vector calculus, so we approximate the curve by this tangent line. And in vector calculus, you approximate a surface by the tangent plane. So the linear approximation to the surface near a point is the tangent plane. So I just have to calculate another tangent plane. That's problem 7. I have the function f of xy equals x plus y e to the xy. And at the point 2, 0, f of 2 comma 0 is 2 plus 0 e to the 2 times 0, which is 2. So I'm looking at the level surface, f of xy equal 2. And the point 2, 0 lies on that surface. What is the gradient of the function f? If I differentiate this with respect to y, if I differentiate this with respect to x, I get 1 times e to the xy plus y times the derivative, it's the derivative of x plus y, which is 1 with respect to x times e to the xy, times x plus y times the derivative of e to the xy with respect to x, which is y e to the xy. And if I differentiate this with respect to y, I get e to the xy plus x plus y times the derivative of this with respect to y, which gives me an x e to the xy. So this is e to the xy times 1 plus xy plus y squared, e to the xy times 1 plus xy plus x squared. That's the gradient. So the gradient of f at the point 2, 0, the exponential is 1, I get 1 plus 0, just 1. And when x is 2 and y is 0, I get 1 times 1 plus 0 plus 4. That's 5, 1, 5. So the gradient of f at 2, 0 is 1, 5. So my tangent plane is, the tangent plane at the point 2, 0 is 1 times x minus 2 plus 5 times y minus 0. So that's x plus 5y minus 2. So this function, let me call it g of xy, is the approximation. This is the linear approximation to the to this function at the point. This is the linear approximation to f of xy. Tangent plane approximates the function. x is 2 and y is 0, we get 0. Yeah, exactly. Sorry. This is the tangent plane plus 2. It's really x plus 5y. It's the linear approximation. And x is 2 and y is 0. It's 2. And so what we can say is that x plus y e to the xy is approximately x plus 5y, where xy close to the 0.20. That's the linear approximation. Problem 8 is a double integral. Already given, sorry, problem 8, we have the integral from 1 to 3, the integral from 1 to e to the x over y, dy dx. So this is the integral from 1 to 3. We integrate with respect to y, x is like a constant, I can take that out. The integral from 1 to e to the x, 1 over y dy dx. The integral of 1 over y is log y, and we're evaluating it from y equal 1 to y equals e to the x. This is the log of e to the x minus the log of 1. The log of e to the x is x, and the log of 1 is 0, so this is just x. So this is the integral from 1 to 3 of x times x, or x squared dx, which is a third x cubed from 1 to 3, which is 27 over 3, 9 minus 1 over 3. So it's 26 over 3. Right. Problem number 9, we have a vector field F equal to 2x, 2y, and prove this is conservative. Well, one condition for a vector field to be conservative is the following. Suppose we have function phi of xy. The gradient of phi is the partial of phi with respect to x, comma, partial of phi with respect to y. So that's some vector field F. And so if we write F as F comma G, then the first coordinate, little f, is the partial of phi with respect to x. And the second coordinate, G, is the partial of phi with respect to y. But then if you take, so if f is conservative, then f and g have this form for some function phi. But then if you notice, if you take the partial of f with respect to y, that's the derivative with respect to y of the derivative with respect to x. And if you take the partial of g with respect to x, that's the partial with respect to x of the partial of f with respect to y. And the order in which you take partial derivatives doesn't matter if your function has continuous nice second derivatives. So these are equal. So if f is conservative, so if f equal fg is conservative, then the partial of f with respect to y equals the partial of g with respect to x. And in fact, for us, that's a necessary and sufficient condition. So if this is the case, the field is conservative. So here is f, and here is g. Partial of f with respect to y, that's the partial derivative of 2x with respect to y, is 0. Partial of g with respect to x is the partial of 2y with respect to x, which is 0. So these are equal. So therefore, this is conservative. So there's a function phi where the partial derivative of phi with respect to x is 2x, which means phi of xy is the antiderivative of 2x with respect to x. That's x squared plus a constant, but the constant is constant with respect to x, some function of y. So I have phi of xy is x squared plus some function of y. And the partial of phi with respect to y is the partial is the derivative of psi of y with respect to y. And the partial derivative of phi with respect to y is 2y, which means psi of y is the integral of 2y, which is just y squared plus a constant. You take the constant to be 0. So if I take the phi of x equal to, phi of xy equal to x squared plus y squared, the gradient of phi is 2x, 2y, which is equal to f. So I solve my problem. F is the gradient of phi, where phi is x squared plus y squared. That's the story. Problem number 9, we just did. Problem number 10. We have the straight line. Oops, from 0 to 3, 4. So I have my curve C, which is the straight line from 0, 0 to 3, 4. You can parameterize it in lots of ways. The simplest might be R of t is equal to 3t comma 4t, as t goes from 0 to 1. And we want to compute the line integral of the scalar function xy cubed ds along this curve. So this is the integral from 0 to 1 of my function. So what is my function? My function, f of xy, is equal to xy cubed. So as a function of t, f of x of t, y of t, x of t is 3t, and y of t is 4t, so that's 3t times 4t cubed. So 4 cubed is 64 times 3 is 192 t to the fourth. So this is f of t. This is my function f of t. Along this curve, along this line, the function is a function of t is simply 192 t to the fourth. If this is r of t, 3t, 4t. R prime of t is the tangent vector you get by differentiating the x and the y coordinates. So the length of r prime of t is just the length of this vector, which is 5. So this becomes the integral from 0 to 1 of 192 t to the fourth times 5 dt. That's 192. The integral of 5t to the fourth is t to the fifth, evaluated from 0 to 1. So the answer seems to be 192. In problem number 11, we have a vector field F, which is conservative. It's the gradient of the scalar field x e to the y. That is, it's the gradient of phi, where the scalar function phi of xy is x e to the y. And we have the curve C, which is given by, or parameterized by, cosine t sine t, for t between 0 and pi. This is just starting at the point 1, 0, and going around the unit circle and ending at minus 1, 0. So my curve C is this semicircle. And the integral around the curve C of f dot dr by the fundamental theorem for line integrals says if you have a conservative vector field, this is just equal to the difference between the vector field evaluated at the endpoints, the potential function evaluated at the endpoints. So this is phi at minus 1, 0 minus phi of 1, 0. This is my function phi, and x is minus 1 and y is 0, you get minus 1. When x is 1 and y is 0, you get 1, so it's minus 1 minus 1. So the answer is minus 2. Okay. And then the final problem is Green's theorem. So we want to compute the integral around a certain closed curve C of xy squared dx plus x squared y dy, where C is the triangle with vertices 0, 0, 2, 0, and 0, 2. And we have to go around this curve in the positive direction, which is the counterclockwise orientation, which means going like this. So with this notation, xy squared dx, x squared y dy, my vector field F is given by f of xy is xy squared, x squared y. And what is the integral as I go around this? So let me do it in a couple of different ways. So we know by Green's theorem that the integral, this integral, f dot dr, just another notation for the same thing, is the double integral around over this region R, this triangle, of the curl of this function. So in this function, the first coordinate f is xy squared, the second coordinate g is x squared y. The partial of g with respect to x is 2xy. The partial of f with respect to y is 2xy. So this is 2xy minus 2xy. That's 0. So I'm just integrating 0. So the answer is 0. And I'm done. We're done. You can also observe that the vector field F is conservative. In fact, if I let phi of xy be equal to a half x squared plus y squared, the partial of phi with respect to x is, oops, that's not right. Sorry. I want to make this phi of xy to be equal to a half x squared y squared. So the partial of phi with respect to x is xy squared. Partial of phi with respect to y is x squared y. So the gradient of phi is x y squared, x squared y, which is exactly f. So this vector field is conservative. And what I know from any conservative vector field is if you integrate around a closed curve, you get 0. So f conservative means the integral around any closed curve, f dot dr, is 0. So that's another observation that allows me to solve this. And I could do it the long, hard way. I could write this path as a union of 3 paths: horizontal line, diagonal line, vertical line. Compute those 3 line integrals, I would get 0. Yeah, that's the whole thing. Didn't take too long, actually. Just 1 second. Okay. How are we doing here? Any questions about this? So I will be on Zoom tonight at 7. If you have any questions, I'm going to try to be there tomorrow, but I'm not sure that I can be. But I will also set up a time on Sunday afternoon if you have any last-minute exams or questions about vector calculus before the exam. And the exam is 11:30 on Monday morning. Any questions before we leave? Someone's asking, when are exams due? Yeah. I need to try to get them in within a couple of days of the exam. Okay. If there are no questions, enjoy the day. It seems to stop raining, and see you all face to face on Monday morning. Bye all.